I'm Seema and welcome to part 9 of the chapter, The Solid State. We now know that there are two types of voids in CCP and HCP kind of packing. The tetrahedral void and the octahedral void. Let us understand where exactly are these tetrahedral voids and the octahedral voids placed in a unit cell or in the crystal lattice. In order to understand that, I have drawn this unit cell and I've taken the unit cell, which is a face-centered cubic kind of a unit cell, and using this I'll explain the presence of how you can locate, or how you, as you know, that all this arrangement is actually all imaginary. The corners of the cube are, or the lattice points here, are only the centers of atoms. And therefore these lines that join to make the cubic lattice, those lines are all imaginary. But yet, where a void would be present, that can be determined if we know this unit cell and we have an idea of where these atoms are present, and we can find out the position of these voids. As you know, tetrahedral voids are formed when you have three balls like this, and they are being covered by one ball. A ball that covers the void. If you hold three balls like this, you get a void in the center, an empty space. The ball that covers this results in the formation of a structure where you have a triangle and a triangular pyramid, you could say. And if you imagine the centers of all these four balls, the shape that you get is that of a regular tetrahedron, right? So we look for these tetrahedral voids, and octahedral voids are formed when you have a void like this between three balls, and there's another three balls that is there, and they also have a void between them. And if you place these in such a way that there is one here and two down here, and if you have two up here and one down there, wrapped in such a way that you had two down and one up here, if you had in this triangle, if you have this one here between the two and the two up here, the void that is formed in this structure is a double void, a void falling over a void, and that is known as an octahedral void. If you do not, I cannot show it like this when I hold it in my hands, but if you do not understand this, please view, I would encourage you to view the previous videos where I showed you all the kinds of voids when I was arranging the hexagonal close packed structures, and I showed you the arrangement of different layers. But we know that the two voids, that is the tetrahedral void, is formed where a tetrahedron has 4 corners and an octahedron has 6 corners, or 6 points between which there is an empty space. Therefore, that space is known as an octahedral void. So, if you really look, this could be an octahedral void where these are the 3 balls in one direction, 2 balls on this side and 1 here, and in the next layer you can have 2 balls over this and 1 ball where you have the 2 balls. So they fall over each other to give you a void which is octahedral in nature. Because if you twist it and hold it in a way, this is the structure that you would get. So when you are supposed to locate these tetrahedral and octahedral voids in the unit cell, how can we do it? Imagine that this is a face-centered unit cell. I have tried to draw the diagram so that you can get an idea of the different walls if you just pay attention to it. The different walls that I have made, I have tried to make them of different color. The front wall is blue, the back wall is pink in color, the sides, the 2 walls on the sides are shown by purple lines, the walls on the top and the bottom I've shown you by these brown lines, and if you notice these green lines that I've drawn in the center, the green lines are actually intersections to the cube. If you imagine this to be the cube, like I've tried to make it, every side is of a different color, and I divide this cube completely from this side, and this side, all 3 directions, that is along the x-axis, along the y-axis, and along the z-axis. I have cut the entire cube and divided the entire cube. One cube has been divided all over throughout to give me 8 cubes, right? So because there are 8 corners, so I have 8 small cubes, and the small cubes can be seen with these green lines. That this is, imagine the green lines to be walls cutting the entire cube all across. Why have I done it? In order to find the location of the tetrahedral void. Now, if this is the entire cubic lattice where you have face-centered cube, let us see how is it face-centered. All the corners are occupied by these black spots, that is the centers of atoms, and each wall, if you see the center of each wall, the back wall was pink, so the center of the pink wall, the front wall is blue, center of the blue, the sides are purple, so you see a center of the purple, and the bottom and the top are brown, and you see the center. So every face, the center of every face has an atom in it. The center of every face and the corners all have atoms. So where do you not have atoms? You have atoms, this is there, this is there, this is there, this is there, if I see one side, and this is there. So this and this actually do not exist in the structure that I have taken. But in a Rubik's cube, I cannot push them out, so it remains in the structure, because here you'll imagine only the line. And there is no atom here, but the lattice points are every face, the corner, center of every face, and all the corners are occupied, and this is the same on all sides. So where will I find a tetrahedral void? I'll cut this entire cube lengthwise, breadthwise, and heightwise. Always I will cut it, and I'll get 8 small cubes now. You see, one in the front, one in the back. This green line divides them 1, 2, 3, 4, 5, 6, 7, 8. There are 8 small cubes that I have now. So if I look at one small cube which I have divided, so let us take this portion, this small cube. How many atoms does it have? It has this one. This one is in the back, you see. This one is in the cube in the back, because the pink wall was in the back. So I have cut the cube midway, the green line here. So the purple line, this side of the purple line, this half belongs to the front, and the pink is in the back. So if this is the cube that I imagine in the front, the purple one, I've extracted the cube here, and I've drawn this structure here. It has one atom here, and this is the purple spot which is empty, that is this point which is empty. So you had this point here is occupied, this spot is empty, and then this top spot is, we come here, it's in the half. So this point is the face center on this side, so that is occupied, the face center. And if you come to the front now, to the front here, this point is the face center here, so that is occupied. And in this cube, if you really look, the face center in the bottom here, this face center is also occupied. So you have face center here, and face center here. That makes 3 atoms, the 3 balls that I showed you, these 3 balls. Okay, they are forming, let us imagine that these 3, if I make a triangle between this point, sorry, I was showing you this side. So if I make a triangle between this point, and this point, I'll get a triangle. And if I extrapolate that triangle, that forms the base. And if I extrapolate, then I have one atom at every corner. So that atom becomes the basic triangle here, and this atom on top makes it a tetrahedron. So that space that you have between these 4 atoms, that is between 3 faces and 1 corner, that is a tetrahedral void. And since you have 8 corners, such a tetrahedral void would be present at every corner of the unit cell. Because in every corner, you can get such a relationship where you have 3 face centers, 1, 2, and 3, and this becomes the tetrahedral void. 1, 2 in the back, and 1 face center here, 1 center here, and 1 face center here. This will become, and this becomes the top. So you'll see, for every corner, you will get a tetrahedral void between the 3 atoms of the face centers around that corner and the corner atom. They together will form a tetrahedral void. What is the number of atoms in a unit cell? The number of atoms can be calculated by counting the total number of atoms. We know there are 8 corners and atoms present in 8 corners. And each atom contributes 1/8, because every corner is equally divided by 8 unit cells. So 8 corners into 1/8 is equal to 1 atom. And there are how many faces? There are 6 faces. And out of the 6 faces, each face, now this blackboard, face center means that it is in the center of the wall. So this wall is divided equally by how many rooms? It is shared by how many rooms? A wall is shared by 2 rooms. A corner is shared by 8 rooms. So any ball which is or atom which is on the center of a wall or a face center will be equally shared by 2 atoms. So its contribution is only half. It is contributing only half to the room. So half of, out of 6, half of their contribution comes out to be equal to 3 atoms. So in a unit cell, that is face-centered unit cell, the total number of atoms is 3 plus 1 is equal to 4. So we know that there are 4 atoms in a unit cell which is face-centered cubic. And we have also studied that if you have, whatever is the number of atoms, the number of tetrahedral voids is always double of the number of atoms. So if there are 4 atoms in the unit cell, the number of tetrahedral voids, how many have we counted inside the unit cell? The 8 corners, each one has a void, and that void is present inside the unit cell, so it completely belongs to this unit cell. It is not shared by any other unit cell. Therefore, there were total number of atoms in the face-centered cubic unit cell is 4, and the total number of tetrahedral voids is 8. It is double of the total number of atoms. Now we understand that, so this is how we locate the tetrahedral voids. Move on to octahedral voids. I told you the shape of octahedral void. You can imagine this to be a triangle that is upright and which is covered by a triangle that is pointing in the opposite direction. So when they join together, they result in the formation of an octahedral void. There is another way of looking at this structure. Instead of imagining that a triangle pointing upwards and a triangle pointing downwards, like I did here, if you imagine, these 4 atoms, any 4 you take, to be a square. Imagine them to be a square. This one is a square. Then if I hold it like this, you will see that if the center you have a square, in the center I have a square and 1 atom on top and 1 atom in the bottom. So there's a square here, and if you make lines for 1 atom on top and 1 on bottom, you can imagine the octahedral shape to be that also. So it's basically the same shape. It is how you look at it. If you twist the entire image slightly, you'll get a feeling that it is a square, or you can imagine it to be a square pyramid. A square, do you see? This is a pyramid, a pyramidal shape. You have a square in the bottom, and if you imagine these to be planes, they would be the 4 planes. If I have 1 ball under this would another be a second pyramid with the same base, but now the pyramid is pointing towards this direction. That is also an octahedral shape. So you have octahedral voids also in the unit cell. So using the same structure, let us see where are the octahedral voids. The octahedral voids, if you really look, the first for octahedral void, you need 6 atoms. And these 6 atoms should be pointing, 1 triangle pointing upwards, 1 triangle pointing downwards. So let us look at the 6 face-centered atoms. Okay, if you imagine these 6 face-centered atoms and you imagine this face center, this face center, this face center. Okay, imagine this to be 1 triangle. And then imagine the other three face centers, this face center, this face center, and this face center, to form the second triangle. So you had 1 triangle which is like this and 1 triangle which is like this. So both the triangles would be opposite and they would be in the opposite directions, and they would result in the formation of an octahedral void. Or if you imagine that to be a square, imagine this structure to be a square. So this turns out to be a square, and this center and this center here, this center here and this center here. You imagine the square in the middle and the centers on top. This results in the formation of an octahedron too. Do you see the octahedral shape here? A square with 1 atom on top. So this becomes the square in the center, and this is the top and this is the bottom. It's like a pyramid, a square pyramid going upwards, a pyramid coming downwards. That is an octahedral shape. So you get one octahedral void right in the body center, because there is no atom in the center of the body. This is a face-centered cubic unit cell. There is no atom in the center. If there is no atom, it means there's a void. So what is the shape of the void? The shape of the void you can get from this, that these are four atoms here, one going on top to make a pyramid on top and one coming down to make a pyramid in the bottom. So that results in the formation of an octahedral void. Then where else in the unit cell do you see a void? Where else do you see an empty space? I see voids in the center of every corner. Do you see? Every corner, the center, I told you this is not an atom. This is an imaginary line that is joining these two atoms. Which points are occupied? The corners are occupied and the centers are occupied. So every edge center is an empty space, which means every edge center is a void too. So you have, how many edges does a cube have? A cube has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It has 12 edges, right? So 12 edges are there in a cube, and at each of the edges too, you see there is an octahedral void. How will you see that? If you imagine that the octahedral void, you imagine this face-centered ball, and you imagine the two corners and one face center. That is, I imagine this and one face center in this unit cell. This atom and the face center, they form, let us say, one triangle. Then in the adjacent atom, you will have in front of this, you will have instead of this, you will have two face centers there and a third face center, which will then form the opposite triangle. Unfortunately, I could not find a structure where I could hold this and show it to you in the lattice. But if you see the extrapolated diagram in your NCERT textbook, you might be able to understand that 3 of these, and then 3, if you project these in front, you will get another triangle which is in opposite direction, giving it the same octahedral shape. Which means that every corner edge center is also an octahedral void. Now, just as when we were talking of the octahedral void which is present in the body center, if an octahedral void is present in the body center, the entire void belongs to the unit cell. But what about an edge? An atom which is present, or any edge, the edge of this room, imagine, I told you this wall is shared by 2 rooms. But what about this corner, this edge? This edge is shared by 4 rooms. Every corner is shared by 8 rooms. And the edges are shared by 4 rooms, because on this floor, the room behind it, the room on that side, and the room on that side, there will be 4 rooms which will be shared by this one edge, or this one edge will be shared by 4 rooms. So such a void which is present at the edge center will also be shared. That void will be shared by 4 rooms too. If an atom, if an occupied lattice point can be shared by those many rooms, then an empty space present in that location will also be shared by those many rooms. So we say that inside a unit cell we have one octahedral void in the body center, and in all edge centers we have 12 edge centers and we have 12 voids. All of them are octahedral. But since every void at the edge center is equally divided by 4 rooms, the contribution of each void would only be 1/4 in one room. Since its contribution will be 1/4 in one room, then there are 12 edges divided by 4. You get only 3 voids for that room or that unit cell. If you get only 3 octahedral voids for that unit cell, what had we studied again? The relationship between the number of atoms and the number of voids, octahedral and tetrahedral voids. We said whatever is the number of atoms, the number of tetrahedral voids is double of it, which we verified. And we also have studied that whatever is the number of atoms, the number of octahedral voids is equal to that. So let us verify that too. So what is the total number of octahedral voids we have? 1 is from the body center and 3 in all from all the 12 edge centers. A contribution is of 3, therefore 3 plus 1 means 4, and we have 4 voids. And how many atoms did we have in the unit cell? The number of atoms in face-centered cubic unit cell is also 4. And the number of octahedral voids is also 4. So this verifies that statement that the number of octahedral voids is equal to the number of atoms in the crystal lattice, and the number of tetrahedral voids is double of the number of atoms in the lattice. So I hope you understand this topic well now, and with this I'll finish this video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.